In Chapter 9, we learned how to determine if a bond is polar or nonpolar by looking at the electronegativities of each of the atoms involved. Now we want to do a bigger picture view and decide if a molecule is polar or nonpolar. Basic rule is that molecules are polar if your dipole moments of each bond add up to a net dipole moment. Now, there are two possible scenarios here. One is that you have nothing but nonpolar bonds. Let's say you had nothing but carbons and hydrogens, you'd have a bunch of nonpolar bonds, automatically you have a nonpolar molecule. If you don't have any dipole moments to begin with, you can't have a polar molecule. So that's really, really easy. If you do have polar bonds, however, your molecule may or may not be polar. It depends on whether your dipole moments add together or whether they cancel out. Basic idea is that you would use vector addition. Dipoles are vectors, and if they cancel out, then this happens when your molecule is totally symmetric. Then there's no net dipole moment, and in that case, your molecule is nonpolar. So if totally symmetric, no net dipole moment, that means you're going to be nonpolar. Whereas if it's asymmetric, you do have a dipole moment, and that guy's going to be polar. So let's look at two examples here. So at the first one, CO2, we can see if we draw the Lewis structure of CO2, the carbon-oxygen bond is polar, but if we look at these dipole moments, they point directly away from each other. They totally cancel out because my molecule is totally symmetric. There's no net dipole moment in that case, so this guy is going to be nonpolar. Now we can look at a really similar molecule, H2O. H2O also has two atoms attached to a central atom, but we can see it's not nice and linear like CO2 is, it's a bent shape. So those shapes from Vesper theory are really going to come in handy here. Because water is bent, its dipoles do not cancel out. See how they don't directly oppose each other? They kind of add up together. So this is an asymmetric molecule, therefore it's going to have a net dipole moment, and that guy is going to be polar. Now, I admit, I am not great at thinking about vector addition without actually doing the math, and a lot of people aren't. So we need a nice, easy way, a nice checklist, if you will, to determine if molecules are polar or nonpolar. So this is how I like to determine polarity. Now, you may notice a theme here, but the very first thing we have to do is draw the Lewis structure. Once you draw the Lewis structure, you can ask yourself, does the molecule contain polar bonds? Again, if it doesn't contain polar bonds, you're good. That guy's nonpolar. You don't have to do anything else. However, if the molecule does contain polar bonds, then you have to ask yourself a second question. Is the molecule symmetric? If it is symmetric, then those polar bonds are going to cancel out and you'll have a nonpolar molecule. So that's what we saw up here in the case of CO2. Polar bonds, but a totally symmetric molecule meant that overall it was nonpolar. If, however, your molecule is not symmetric, it's going to be polar. Now, it can sometimes be a little difficult with these large molecules, octahedral, trigonal bipyramidal, things like that, to determine if it's symmetric or not. So when you look for symmetry, look for two things. One, does it have different exterior atoms? In that case, this is going to be asymmetric. 2, does it have lone pairs? Lone pairs also make your molecule asymmetric, with 2 exceptions, of course. If you have all the same exterior atoms and you have 5 electron groups, so a trigonal bipyramidal electron geometry, but 3 lone pairs, your molecular geometry is linear, and in that case it becomes nonpolar. Similarly, 6 electron groups, that's octahedral electron geometry, but 2 lone pairs, you get a square planar molecular geometry, also nonpolar. Those 2 are pretty rare though, so for the most part, these 2 rules, right, oops, I don't know what that happened. These 2 right here are going to be good. Look for different exterior atoms and look for lone pairs. And if that's the case, you have a polar molecule on your hand. So, let's look at examples. Again, I've cheated, went ahead and drew the Lewis structures. You're going to have to draw those yourselves, but for example's sake, we can go ahead and start from here. So let's start with O3. O3, we can stop right there because we say, oh, these are all the same atom, and if it's all the same atom, in that case, it can't be polar. So this guy automatically is going to be nonpolar because all its bonds are nonpolar. If you have two of the same atom, it's going to be a nonpolar bond. So we don't have to look for anything else. We're done. Next, we can look at SO2. SO2, okay, it does have polar bonds because it's not one of the two exceptions, two of the same thing, or carbon and hydrogen together. So it does have polar bonds. So then we look, okay, does it have different exterior atoms? It doesn't have lone pairs. Well, the exterior atoms are the same. They're both oxygen, but it does have this lone pair here, and it's not one of the two exceptions mentioned above, so it's not symmetric, and therefore this guy is polar. All right, CH2, Cl2. Now, this one's tricky because if we look at it, it looks like it's nice and symmetric. But what we have to keep in mind is that's not the real shape. That's the Lewis structure shape, but really, this molecule... I'm not great at this. Should be a wedge and a dashy. It's hard on a tablet. Really, the molecule looks like this. So it's a tetrahedral. It's not this flat, two-dimensional square like we've drawn here. So this guy is not symmetric. Now, even if we forgot about its real shape here, what we could look at is just the fact that, oh, this guy has different exterior atoms. Different exterior atoms means it's not symmetric. This guy is going to be polar. Another one, CH3OH. This one we can just easily see. Look, we got some lone pairs here. We got different exterior atoms all around the molecule. This guy is going to be polar. Last one, I didn't even draw the Lewis structure. Really, really easy. C6H14, nothing but carbon-hydrogen bonds. Therefore, nonpolar bonds means overall a nonpolar molecule. So, pretty simple. Just as I said, go through this. If you have polar bonds, look for these two things. Different exterior atoms or lone pairs, and then you got yourself a polar molecule.